Math 2414 sequences, video 4, convergence. When we talk about a sequence, then we can also talk about whether or not it's converging to a certain value. For example, and we'll look at this definition in just a second. In fact, let me go in and make some space for this definition, or some space between the title and the definition. And let's say we have the following sequence of let's say 1/2 to the n power. N equals, let's start this one as 0 to infinity. Then it would be really easy to generate this sequence as a set of values by letting the exponent start at 0 and then move upwards. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1/4. 1/2 to the third power is 1/8, etc., etc. But if you look at a sequence through the lens of it's a function, then our function would be f of n equals 1/2 to the n power, and every point in the sequence corresponds to an ordered pair in terms of input and output. When we put in 0 into the function, we get out 1. When we put in 1 into the function, we get out 1/2. When we put in 2, we get out 1/4. When we put in 3, we get out 1/8, etc. So really every point in a sequence, or every value in a sequence, can be thought of as an ordered pair and its corresponding point on a graph. So what would this look like if we plotted all these points? Well, let's get rid of all this and let's plot all those points. Let's see, our first point in the sequence was 0, 1. The 0th position, the value is 1. So if we start marking off some points here on the x-axis, 3, 4, 5, although I guess you could argue that this is the n-axis, since n was representing the input of our function, and our outputs were an. We write them like that, or we could write it like that in function notation. Either way is fine. But they started at 1 and they just got cut in half each time. So let's put some points up here to represent the points in the sequence generated by an equals 1/2 to the n. When we put in 0, we got 1, so we would have a point right there. When we put in 1, we got 1/2. When we put in 2, we got 1/4. When we put in 3, we got 1/8. And then we would get 1/16 and 1/32, and so on and so forth. Almost as if we were drawing a graph. But the main difference here is, in the past when we've drawn graphs, they've been of continuous functions, so we would connect all the dots continuously. A sequence is like a discrete function in the sense that there are gaps between consecutive points on the graph. But it looks like these are getting closer and closer to 0. In other words, it almost looks like the limit as n approaches infinity of this sequence is 0. And that really wouldn't be that hard to argue, because we could rewrite this as 1 to the n, but that's just 1, over 2 to the n. And as n approaches infinity, the denominator explodes, so the fraction collapses to 0. But what does it actually mean for a sequence to converge to a value? Well, and I'm just reading this definition below, a sequence an is said to converge to a real number L. In this case, we're saying our limit is 0. That's what L is for. If we can make an permanently close to an L as we want, if we pick n large enough. What does that mean? That means no matter how close to 0 we want to get, at some point this sequence will go there and beyond. Excuse me. No matter how close we want to get to 0, this sequence will eventually get that close and never be less than that distance from 0. For example, let's say that we wanted to get all the points in the sequence within 2/10 of 0, so 2/10. Now, 2/10 within 2/10 of 0 means that it can be 2/10 below as well. So we're going to set up this little strip, if you will. How about I draw a line here, take advantage of what I can do. And we draw another line here at -0.2. So in this case, what we're saying is as close to L as we want. What we're saying there is within 0.2 of 0. So we open up this strip between negative 0.2, and positive 0.2. And what the end part of the definition says is if we pick n large enough, that means at some point on the x-axis, 1, 2, 3, somewhere, our points will enter that green strip and never leave. In this case, it looks like it's a 3 because once we put in 3, we got 1/8, and 1/8 is a decimal is 0.125. That's within 0.2 of 0. A 2 wouldn't work because that's 0.25. That's not quite close enough. So it looks like 3 is the number that the n has to be at least that large. If n is at least 3, then our sequence will be within 2/10 of our perceived limit, which is, it's not actually perceived, it's the limit. So it's kind of a game of, okay, you say you're approaching this, then if we set up this real skinny strip along what you think you're approaching, that sequence will enter that strip and never, ever leave. Now, there's a little bit more technical definition that I'm going to show you, but I don't want you to worry about it too much. For those of you who are going into more theoretical math classes, real analysis to be specific, then you'll probably see a lot more definitions like this. There's no probably to it. You'll see a lot of definitions like this. So the technical definition is if we say a sequence approaches a limit, that can happen if and only if the following is true. Well, first off, this is the Greek letter epsilon. In upper level theoretical math classes, you talk about small positive numbers a lot, and they're usually called epsilon. Sometimes they're called delta or other Greek letters, but that's the Greek letter epsilon. If you draw it more precisely, it looks more like that, but I just draw it like that. But the technical definition is for every epsilon greater than 0, there exists some n greater than 0, such that little n greater than big N implies the absolute value of an minus L is less than epsilon. Now, what the heck is all this? Well, this epsilon represents that distance that we're trying to get permanently close to. So this represents the a small distance from the limit. And the absolute value of the difference is when you subtract two things and take their absolute value, that measures how far apart they are. So what this little blurb here at the end says, let's highlight this. What this little blurb here says is the distance between where you are in the sequence and your limit is smaller than some predetermined value. In the previous example, that predetermined value was 0.2. So what does all this mean? Well, this just means that there's some boundary by which when you surpass that, your sequence gets in that green strip. In this example, that number was 3. In other words, in this example, our epsilon, if you will, and again, we're not really going to do this much in this class, our epsilon was 0.2. We want to get within that distance of our perceived limit and never leave there. And the capital N was 3. Actually, the capital N could have been 2, because what the definition says is if you go further than this position in the sequence, then you will be this close to your limit from that point forward. But the definition says it doesn't matter how small your epsilon is. I could have made the epsilon 0.1. There would be a point on the x-axis that once I go beyond it, I will stay within that green strip if I make this strip half as skinny as it is now. But the definition says for any positive number, epsilon greater than 0. So the width of this strip here, I can make it 2/10, I can make it 1/10, I can make it 1/100th, I can make it 1/1 so skinny you couldn't even see it. But if the limit actually is 0, then it doesn't matter how skinny that strip is. At some point, it may be way down the road, at some point your sequence will enter that real skinny strip centered at 0 and never leave it. That's what it means for a sequence to converge to a limit. Let's take a look at a specific example and in this video. Determine if this sequence converges. If so, determine its limit. The sequence is generated by the function 2n plus 1 over n, and n is starting at 1. Before we attempt to get an answer to it, let's take a look at some values. Like what would we get if we put in the n values? Starting with n equals 1, we would get 3 on top of 1, so that's just 3. If we put in n equals 2, we would get 5 over 2. Let's use decimals. 5 over 2 is 2.5. If we put n equals 3, we would get 7 over 3, which is 2.3 repeating. If we put in n equals 4, we would get 9 over 4, which is 2.25. Let's push this a little bit further. If we put in 5, we would get 11 over 5, which is 2.2. If we put in 6 right here, we would get 13 over 6, which is 2.16 repeating. If we put in 7 right here, we would get 15 over 7, which is 2. Not everybody knows their sevenths, but I'm not everybody. 2.142857 repeating. That's the first obnoxious repeating decimal. And if we put in n equals 8 right here, we would get 17 over 8, which is 2.125. So what do these numbers look like they're getting closer to? 3, 2.5, 2.3 repeating, 2.25, 2.2, 2.16 repeating, 2 point all that repeating, 2.125. These look like they're getting closer to the number 2. Now, you could argue, are they getting closer to 2.1? And if so, will they ever surpass that? Well, I can give a pretty convincing argument that it's going to go beyond, folks, that it's not only going to hit 2.1 but go below. For example, let's say we put n equals 100. Then the 100th position would be 201 over 100, which is 2.01. So yeah, these look like they're getting closer to 2.1, but I can go below that. Can I ever go below 2? The answer is no, because the limit actually is 2. Now, how do we know the limit is 2? Well, there's a couple of ways to verify that. But one easy way is to take this expression, and if you think about when we integrated using partial fractions, it was a criteria that the excuse me, that the degree of the denominator had to be greater than the degree of the numerator. And if that were ever not the case, then you could use long division or some other trickery to fix that. So let's go down here and look at this for a second. I think I'm going to play with moving me around the screen in future videos. If we look at this, we could do long division, but one typical way to clean it up, especially when the denominator right here is a monomial, is to split this into two fractions, 2n over n plus 1 over n, and then the 2n over n reduces to 2. And then just think about what happens to this fraction as n approaches infinity. Well, as n approaches infinity, that goes to 0, so it stands to reason that the limit is actually 2. All right, in the next video, we'll look at some theorems that will help us determine this, what some sequences converge to, or that the fact that they might not converge, they could diverge. So we'll look at that in the next video.